All right, everyone. So let's take a few minutes here and take some questions from the worksheet that we just checked in. I think that's number 5. Is that right? 4? Something? Some number. The one we just looked at. All right. Did anybody have any questions on 1 through 6? Those should have been relatively straightforward. Okay. Seems like nobody has had any problems there. Let's do a couple from 7 through 15. Does anybody have ones from there? Matthias? 14? Sure. Yeah, go ahead and stand up and turn them off. You're welcome to do that at any time. Okay, so Matthias, the first thing I would do is I'd start by doing a prime factorization for each of the numerator and denominator. Let's see, what do I have there? 3 to the 4th times 7. Okay with that?
Yes.
Okay. Now, since these are different radicals, to be able to combine them, I need to write them in exponential form. So that's going to be 2 to the 3 over 2 and 5 to the 1 over 2. And in the denominator, I'm going to have 3 to the 4 thirds and 7 to the 1 third. Are we okay with that? Okay. So I used this property, right? So if I have the cube root of 7 to the 1st, that becomes 7 to the 1 third, right? Now, I noticed that none of the numbers, or these exponentials in my problem, the base of these exponentials is all different, right? I have a 2, a 5, a 3, and a 7. So none of these exponentials are going to be able to combine. So I'm done with that step. The thing I have to worry about next, though, is that I have fractional exponents in the denominator of this fraction. Remember that a fractional exponent is the same as a radical, and we don't want to have radicals in the denominator, so we need to take care of these fractional exponents. So looking at 3 to the 4 thirds, what I'm going to ask myself is, what's the next whole number after 4 thirds? So it would be 6 thirds, or 2, right? So how many more thirds do I need to get to 6 thirds? 2. So I'm going to multiply the top and bottom by 3 to the 2 thirds. Then I'm going to look at the 7 to the 1 third. The next whole number after 1 third is 3 thirds, or 1. So how many more thirds do I need there? 2 thirds. So I'll multiply the top and bottom by 7 to the 2 thirds. So in my numerator, I'm going to have 2 to the 3 halves, 5 to the 1 half, 3 to the 2 thirds, 7 to the 2 thirds. And the denominator, I'm going to have 3 to the 2nd and 7 to the 1st. Is that okay there?
Yeah.
Okay. I still have a couple more things I need to worry about here. Next thing I'm going to do is look for improper fractions. And notice I have one of those, 2 to the 1, or the 2 to the 3 over 2. So I'm going to rewrite that improper fraction as a mixed number. What is the mixed number for 3 over 2? 1 and 1/2, right? Is that okay?
Yeah.
So what that allows me to do is it allows me to rewrite 2 to the 3 over 2 as 2 to the first times 2 to the 1/2. And then all that other stuff is just going to stay the same. Is that okay there? Okay. Now the last thing I'm going to worry about, the directions for this problem say to write your final answer in the same form as the start. So my final answer should be in radical form. I would prefer if I write this so that I have just one kind of radical in here. If I look at this, I have currently square roots because the denominator is 2. And I have cube roots because the denominator is 3. What I'm going to do is I'm going to rewrite these so I have a common denominator for all of these fractions so I can put them all under the same radical. What would the common denominator be between halves and thirds? Sixths, yeah. So 1/2 turns into 3/6, and 2/3 would turn into 4/6. Okay with that? So I can now put this all under the 6th root, and I'm going to have 2 to the 3rd, 5 to the 3rd, 3 to the 4th, and then 7 to the 4th. And you could leave your final answer looking like this in an exponential form, or you could multiply those numbers together and get just a regular number, but 2 to the 3rd times 5 to the 3rd times 3 to the 4th times 7, that's a big number. I'd probably just as easy to leave it in this exponential form, and that would be fine for me on a test or a quiz or whatever, or your homework. Does that feel okay there? You're welcome. Who else? Are there others from this assignment that we'd like to talk about? I'm happy to do some more. Lexi? For number 10? Yeah. So I just wrote it as 12 to the 3rd times 8 to the 3rd. You could multiply that out and get it just as a one whole number. Thank you. But I didn't do that on when I wrote it, or I did my work, but anyone else with questions from this? Ziton? Number 9? Sure. So typically the first thing I'm going to do is just like I started within the previous problem is I'm going to do a prime factorization. So I'm going to look at the basis for my exponentials. 16 I can rewrite as 2 to the 4th. But 5 is already prime, so I'm not going to do anything to the 5. So when I have an exponent of an exponent like this, we can simplify that by multiplying. So 4 times 5/9 is 20/9. Okay there? Now, when I have an exponent of a product, I remember that that exponent is going to apply to both factors of the product. So I can do that. And then I have an exponent of an exponent again, so those are going to multiply. Oops. And I went ahead and reduced as I multiplied. Okay. Now I need to worry about the negative exponent. So a negative exponent makes a reciprocal. So I'm going to have 1 over 2 to the 20 thirds, and then 5 to the 7 thirds. And at this point, I could either worry about the improper fractions or the fractional exponent in my denominator. I'm going to worry about the fractional exponent in my denominator first, because oftentimes that's going to take care of the improper fraction along the way. So it just saves me a step. So if I look at the fraction 20/3, the next whole number after 20/3 is 21/3, or 7. So I need 1/3 more. So I'm going to do 2 to the 1/3 to the top and bottom. Then if we look at 7/3, the next whole number after 7/3 is 9/3, or 3. So I'm going to multiply the top and bottom by 5 to the 2/3. Tong, are you okay with that? Okay. So the reason that I'm doing this is now in the denominator I have 21/3, or 2 to the 7th, and then 5 to the 9/3, or just 5 to the 3rd. And I have no more fractional exponent in my denominator, which is the same as having like a radical in our denominator, so we didn't want to have that. And the numerator, we just have 2 to the 1/3 times 5 to the 2/3. And this is the same form as we started with the fractional exponent. So I'm just going to stop there. You could multiply out 2 to the 7th times 5 to the 3rd if you wanted to and just turn that into a regular number, but it's fine the way it is also. Okay. So what this step is allowing me to do is if I multiply these two together, I add their exponent, which is giving me no more fraction in my exponent. Can you see that? So I'm doing, these guys are going to multiply together, and then those ones are going to multiply together. Is that? Okay. And that gets rid of the radical in the denominator issue. Okay? You're welcome. Probably have time for one more if anyone else would like to talk about one of these. Okay, fair enough. That's fine. So let's start today. We're going to be talking about solving radical equations. And this is going to be part 1. We'll do this at least 2 days. We'll kind of see how it goes. So some things to remember, some important facts that are going to be of particular use to us when we're solving. So I have 2 of them. The first one is So the first thing is that when we take the even root to both sides of an equation, that's going to create a plus or minus. So for example, if I just have something like x to the 4th is equal to 16, to get rid of the 4th power on the x, I can take the 4th root of both sides. But because this is an even root, That's going to create a plus or minus. Okay, so we have to be careful there. So the second item is that when we're solving an equation that includes a even root, we have to make sure that we're checking our answers for extraneous solutions, as those can occur when there's an even root in the original problem. And we'll look at some examples, not today of this happening, but later on we'll see some examples where that can happen. Okay, so let's just kind of run through some examples of this solving process here. So let's say we have the cube root of 2x plus 7 equals 3. What's the first thing we should do here? So we're trying to solve for x. In general, when we're trying to solve for x, we're following the reverse order of operations. Well, before I can divide by 2, there's something else I need to do. Yeah, we need to get rid of that cube root. And Louise says to do that, we can cube both sides of our equation. Then that cube is going to cancel out the cube root. Notice that 3 to the third is 27. One of the common mistakes I see the students make in this course is that they confuse an exponent with multiplication. So 3 to the third is not the same as 3 times 3. So we have to be careful there. Now that the radical is gone, this is a pretty easy problem, right? What would I do next? Subtract 7. And then we would divide by 2. Do I need to check this problem? Do I need to check this solution? If I go back and I look at my original problem, this is an odd root. So no, I don't need to check it. Is there any harm in checking it? No. So if you're uncertain, you should go ahead and check them, but the odd ones we don't need to. Everybody okay there? Let's do another. Let's say we have 2 times the square root of x plus 10 minus 6 equals 10. What's the first thing I'd want to do to solve this equation? Any ideas? So the first thing I'd want to do is to isolate the radical part. So I'm going to begin by adding 6 to both sides. Next thing I would want to do is divide by 2. The next thing would be to square both sides to cancel the radical. And then lastly, we would subtract 10 and get that x is equal to 54. Should I check this problem? Yes. Why should I check this problem? Yeah, the original problem is an even root. So 2 times the square root of 54 plus 10 minus 6 should equal 10. So if I do that, 54 plus 10 is 64, and the square root of 64 is 8. And 2 times 8 is 16, and if I subtract 6 from that, I do get 10. So this answer is correct and not extraneous. Everybody feel so far so good? Shouldn't be too bad. I think it's rather similar to solving the absolute value equations that we did in first semester. The difference being that the way we cancel a radical and the way we cancel the absolute value are different. But overall, the strategy is fairly similar. What if we have 4x to the 2/3 is equal to 36? It's the first thing I'd want to do here. Well, I want to get the x by itself. So I should divide by 4, right? We're trying to isolate the radical. In this case, the radical is that fractional exponent. Oops. And now, how am I going to cancel out that 2/3 power on the x? I'm sorry, what did you say? Well, multiplying by 2/3 isn't going to cancel a radical, right? That's going to apply only to the base of the exponential. If I multiply the reciprocal, again, that's not what I want, but you're on the right track. It's not multiplication, though, that we need to do. I want to use an exponent to both sides, because remember, when I have an exponent of an exponent, what happens there? Now those exponents multiply, right? And 2/3 times 3/2 is just 1. And 9 to the 3/2 is 27. You could type that into your calculator if you needed to, but it's not hard to do by hand. A prime factorization is all you really need there. Now, do I need to check this answer? Well, in the original problem, this is an odd root, so we don't need to check this, but we did make another mistake here somewhere. Does anybody see what the mistake is? Square rooting the 27. No. We're not multiplying. That's an exponent. That's 9 to the third, and then square rooted.
Okay.
But that is the square rooted part is the issue. What did we do to both sides here? We did use an even, we did do an even root to both sides, right? Remember, the denominator of a fractional exponent is the same thing as a radical. So really, what should my final answer have here? A plus or minus. So you have to be very careful when you're using those fractional exponents. It's very easy to forget that you just used an even root there. Okay, so be on your toes looking for those situations. Let's do one more here. What should we do first here? Subtract 3. Very good. What next? Okay. So multiplication is probably not the term that you mean there, because multiplying by 3 over 2 would mean this, which is probably not what you mean. So we're going to use the exponent of 3 over 2 to both sides. So that's fine. And when I have an exponent of an exponent, those multiply. And 4 to the 3 halves is 8. Did that in my head, but you could type that into your calculator, or if you did a prime factorization on the 4, it would be easy to see how I got to 8. Hold on a second. I need a plus or minus here. Why do I need the plus or minus? Because I did the even root to both sides. Again, very easy to forget to do that, so you have to be on your toes, especially with these fractional exponent problems. Okay. Now we can subtract 2 from both sides. What is 2 or plus or minus 8 minus 2? Can I write that as just plus or minus 10?
There's 2.
Yeah.
X equals -10, X equals 6.
Yeah, exactly right. So we have to write as -2 plus or minus 8, which allows us to write it as 6 and -10. Is everybody okay there? Do I need to check this problem? So if I go back and look at the beginning, that's an odd root, correct? Do I need to check that? No. So I have 2 solutions here, positive 6 and -10. Okay. So as an aside here for this question, this is something that kind of always comes up. Can I do the following? If I have x plus 2 to the 2/3, can I just write this as x to the 2/3 plus 2 to the 2/3? Is that allowed? This is just like an aside. What do you guys think? Is it okay to do that? No! No, that is always wrong. That's very bad. So, in general, that is not true. In the business, we refer to this as the freshman's formula because it's a silly mistake that untrained mathematics students make, aka freshmen. And you might say, well, hold on a second, Mr. Kulik, wait a minute. We had isn't that one of the properties? No. This is one of the properties that exponent can apply across a multiplication symbol, but it does not apply across an addition or subtraction symbol. And that's a very important distinction and a place that, stop talking, please, a place that students frequently make mistakes. And it's a rather critical one because it's never true, right? You can never do that. There's never allowed. So please be very, very careful there. That distributive property that you're trying to apply is a very special property and not one that happens very often. In fact, until you take like a calculus course, you'll not see another operation that distributes across addition or subtraction like that. Clayton? Sure. Okay. We're going to stop here for today.